Hello everybody. I would like to talk to you about the multi-boson production measured in at loss, measurements including vector-boson scattering and photon-photon fusion. And why do we measure these processes? Well, there are several reasons. It's a great test of the electric sector and provides also tests of the perturbator of QCD. And you are also able to search for new physics at the data electron volt scale. I will be presenting quite a lot of measurements today, as I mentioned, including vector-boson scattering and photon-photon interactions, and its general correction of fundamental searches, precision measurements, and few beyond the standard interpretations. The first measurement I want to talk about is the 4-lepton final state, which is dominated by 3 main processes depending on the invariant mass of the 4 leptons. That would be the single Z production between 16100 GeV, displayed here at the top. Then a Higgs production around 105 GeV, displayed here in the middle, and then ZZ production, which is on show when you go over the mass of 2Z boson, so over 180 GeV. And the remaining 4-lepton invariant mass regions are then dominated by the off-shell ZZ production. And in these 4 main regions, so the single Z, Higgs, and off-shell, on-shell ZZ, define 4 regions where the measurement is performed. And the paper then provides large number of differential distributions, including, for example, invariant mass of the 2 lepton pairs, or distance in rapidity. And overall, the main limiting factor of for these distributions is that they are dominated by statistical uncertainties. All the distributions are then unfolded to the particle level, where a Brand-folding efficiency correction is applied for each of the 4 lepton, and this should then minimize the dependence of the standard model description of the lepton kinematics. I'm just showing here 2 examples. For the ZZ on shell kinematic region, and specifically I'm showing the diaphragm masses, which as expected for the on-shell region, both peak at around 90 GeV to 100. The paper also presents the fiducial cross-section in all 4 regions and in the combined phase space, which is then combined to Sherpa-Pohak, showing quite a good agreement between the measurement and the prediction. And finally, the paper presents the most precise measurement of the branching ratio of the Z to 4 leptons, displayed here, which once again is in agreement with the prediction. The final point is that there are several non-standard model interpretations. First, on the 6-dimensional operators of the EFT. In total, the paper gives limits on 22 Wilson coefficients listed here, both for only the linear term, for the interference, and for the full model, which can give quite different limits. And the second interpretation is for the B minus L, so the baryon minus lepton numbers, symmetry breaking, which then introduces exotic Higgs boson, designated X2 and Z prime. And the paper then offers limits on their masses, as for example here for the X2. The second measurement is W with at least 1 jet, which is the first detailed study of this process. And on top of being generally sensitive to the electric sector, it's sensitive to the analog corrections. And the signal is then dominated by the quark-initiated WW. With dominant background coming from a TT bar, where the normalization of this TT bar background is then estimating using data-driven method based on a region with large number of jets, which are tagged as coming from the hadrons, so-called P jets. Once again, the paper provides quite a large number of differential distributions, which are being compared to various generators, matrix, and Sherpa. I'm showing here again 2 examples. For example, the transverse momentum of the EMU system compared to a large number of the generators, which show quite a good agreement, maybe with some small fluctuations here, which is, however, still well covered by the uncertainties. And here on the right is the PT of the leading jet. The paper then provides a measured cross section, which is found to be 258 femtobarns, which is then again compared to the different generators, showing really good agreement between those. And this measurement is then limited by systematic uncertainties, which mainly come from calibration of the jets and from modeling of the different backgrounds. The paper then provides again understandable interpretation specifically for the anomalous triple gauge coupling and the operator in the 6-dimensional EFT sensitive to it. And yeah, the paper provides limited disclosure parameter CW, both in a linear and quadratic interpretation. And as you can see, the quadratic inclusion of the quadratic effects has quite a large effect. And for this reason, one cannot really neglect the higher orders and the dimensional 8 interference terms. So the validity and the interpretation one can make from these parameters is limited. And the next measurement is then Z gamma final state, where the goal is to mainly measure Z gamma, where the gamma comes from is in the initial state and is not emitted from the final state leptons. And for that reason, the main kinematic selection is on the invariant mass of the two leptons and gamma, which then has to be larger than 182 GeV. And this then excludes the final state emission. I think one really interesting thing about this measurement that it has sizable background from PILAB, meaning that the photon and two leptons can come from different proton-proton interactions. And this starts to be a sizable effect of several percent, which is then the contribution is estimated to data-driven method. I think this is interesting, especially in the future as the luminosity will increase. This will become more and more important, and we need to learn how to deal with this background from PILAB. However, the limitation of this measurement comes mainly again from instrumental uncertainties and from background where jets are misidentified as leptons. The paper again provides several kinematic variables, which are then encoded to the particle level. Here an example I'm showing is transverse momentum of the LL gamma system, again compared to different generators, Sherpa and McGrath, where you can see that in the leading order there is quite a large difference, but once you include the NLO, there is good agreement with the theory, and there is also the measured overall cross section, which is then compared to different generators. Again, good agreement between the prediction and the theory. Now I will talk about one vector-boson scattering measurement in the Z+2 jet's final state, which is displayed here. You have two quarks which then scatter through to W's, which then scatter to Z's. And this is important measurement because the presence of the Higgs boson in the standard model cancels divergences in this production. So it's a fundamental test of the electroweak symmetry breaking. And it can be also sensitive, for example, to anomalous ZZ to ZZ coupling, which is not present in standard model at 3 level. And it's quote pure electric process, so there's no direct color flow between the protons or quarks, which can be compared to the dominant background, which comes then from a QCD production, displayed here at the bottom. And for that reason, the BBS electric production has quite different kinematic properties. For example, larger rapidity separation between the two jets and larger invariant mass. So yeah, as I mentioned, I will be showing the Z+2 jets final state, but for those interested, there's, for example, order Z gamma plus time jets measurement linked here. This Z+2 jets observation was measured in two final state with 4 leptons and 2 leptons and 2 neutrinos, where the advantage of the former is that it allows full kinematic reconstruction, and that makes discrimination from the backgrounds easier. The main selection, which separates this process from the QCD background, then requires large invariant mass and large rapidity separation. The QCD background, its normalization is then estimated through data-driven method, by forming control regions with reversed requirement on the invariant mass and on the rapidity, as shown here at the bottom. And a specific BDT is then trained to distinguish between the electroweak and QST production in the two final states, where especially here for the 4 lepton final state, you can see quite a nice discrimination between the two. And in the end, these two processes were measured and observed with 5.5 sigma significance, though yeah, they are still statistically limited. And here you can find the measured cross-section compared to standard model correction, and within the uncertainties they show a good agreement. And the final thing I want to talk about shortly are photon-induced processes, which are again great probes of the electroweak part of the standard model, especially since at the leading order they do not involve any strong interactions. The protons can remain intact. And the reason we are able to study them at the LHC and Atlas at all is because, of course, protons and heavy ions are charged particles. And when they are boosted, their electromagnetic field then behaves as a field of quasi-real photons, which then interact. But because it's pure electric interaction, there is low particle activity, which can be then used to distinguish these events from background. In case of the analysis I'm showing today, so gamma gamma to WW and gamma gamma to 2 leptons, where both have 2 leptons in the final state. You have background from, depending whether you are on the same flavor or different flavor, from Delian to 2 leptons or from WW to 2 leptons, where these two processes, they can inclusively have extra tracks from underlying event, ISR, and for that reason, you can distinguish these two by rejecting events with additional activity near the vertex. So we look at the tracks of the 2 leptons, reconstruct the vertex, and if there is additional track from our central detector, we reject such an event as coming from background. The first measurement I want to talk about is gamma gamma to WW observation, published recently, which is unique probe, especially of the quartic vertex of 2 photons and 2 gammas, which was studied in events with low multiplicity of tracks, as I have mentioned. However, the property multiplicity of tracks is something which is not well-modeled property in our background, and we had to derive a data-driven corrections to the underlying event and to our pilot. And then the signal and our backgrounds were fitted in several control regions, and in the end, this process was observed with 8.4 sigma significance, with measured cross-section of around 3 femtobarons, with results consistent with the standard model prediction. And yeah, the main limiting factors right now is modeling of the main background coming from inclusive WW, and statistical uncertainty coming from our data-driven background, mainly from jets is identified as the leptons. And here on the right, you can see how well we get separated. So this is in region with 0 additional tracks. And once you get a slightly higher transverse mass, you are dominated by our seal here in the line. And the final measurement is not a multi-boson final state, but it's still interesting to mention it. Because in general, these photon-photon processes, even though they are interesting, they suffer, among other things, from uncertainties coming from modeling of interaction between these scattered protons. So the protons can scatter, they can even dissociate, and this is something which needs to be studied in more detail. And to do that, you need to tag the proton, and that can be done on Atlas using AFP or Atlas for proton spectrometer. And how do you do it? You can measure the energy loss of the proton. In the AFP, you simply measure the proton energy, while in the central detector, where you only measure the 2 leptons, you can estimate this energy loss through this formula, which depends on the invariant mass of the 2 leptons and on their rapidity separation. And by requiring some selections on these two, you can then match a dilepton pair with scattered proton and measure the proton scattering in these processes directly. this was then consistent with the standard model, and it's something which can be then used in future, for example, in more detailed gamma gamma 2 WW measurement. So to summarize, Atlas has quite a rich multi-boson program, including precision measurements, observations, and beyond standard model limits. And it generally is a great way to study the electronic part of the standard model. And yeah, I have shown you quite a lot of measurements, including the SM limits on the FT, for example, on the gamma gamma to double level correction.